Hello YouTube, welcome back to BitBite Network, the go-to place for all things programming and Java. Today we have a topic that's crucial for any Java developer, which is ArrayList, LinkedList and Array. In this video we will dive deep into the differences between this data structure, exploring their strengths, weaknesses and the scenarios where each shines. Whether you are a beginner or an experienced coder, understanding these nuances will elevate your programming game. So, grab your coding mug, hit that like button, and let's jump into the world of array, ArrayList, and LinkedList. Let's begin with the initial distinction, member access. Starting with a dive into Java's fundamental building blocks, arrays. Arrays serve as the versatile tool in Java programming, offering a straightforward yet potent functionality. Accessing the members of an array is easy. Just use those square brackets. It's like opening a data treasure chest. For example, to access element at index 3 here, we can use the square bracket mentioning the index number. It's that simple. Now, let's shift our focus to ArrayList and LinkedList. These dynamic duos are not just any data structures, they are the rock stars of Java's collection framework. They come armed with a set of methods that allow us to not only access but also modify elements seamlessly. For example, to add car type to existing list of car here, we can just use add method. On one side we have simple arrays and on the other we got the powerful duo of ArrayList and LinkedList armed with methods to handle collections. Let's dive deeper into these differences and see which one suits your coding adventures the best. Welcome to the next difference, which is memory storage, where efficiency of data organization comes into play. As a data structure, efficient storage impacts performance. How we organize data in memory influences how quickly and effectively we can access and manipulate the data. Choosing the right storage strategy is crucial for optimizing program efficiency. That's why we always consider space efficiency in any algorithm. Let's continue with the memory storage. Elements in array are stored in a contiguous block of memory, whereas ArrayList and LinkedList are not a contiguous block storage data structure. Let me explain what it means in the next slide. First up, we have arrays. Picture arrays as neatly arranged like books on a shelf, occupying a contiguous block of memory. This sequential arrangement facilitates rapid access and systematic retrieval. Now, let's shift gears to ArrayList and LinkedList. First, we will start with ArrayList. Unlike arrays, they don't adhere to the contiguous block storage principle. Instead, think of them as a network of interconnected nodes. ArrayList uses a dynamically resizable array, maintaining its element in a more flexible structure. But note one thing, behind the scenes, the ArrayList manages an array to store references to objects. And the array is contiguous, meaning the memory location for the references are next to each other. However, the actual objects might be stored at different memory locations in the heap. This is the characteristic of an array list where the underlying array is contiguous, but the objects it refers to may not be contiguous in memory. Let me explain with some example for better understanding. I got a visual representation here that will shed light on what's happening behind the scenes. Picture the array list as a container, and within that container we got an array, a structure lined up of references. As you can see, on the screen. Here is a array list represented as a box. Inside that box, we have an array, and this array is contiguous, meaning the memory location for references are right next to each other. Now let's zoom in a bit. Inside the array, we have got individual boxes representing references. Let's call them ref1, ref2 and so on. These references are like pointers that guide us to the actual objects stored outside the array. And voila, down here we have got the actual objects, obj1, obj2 and so forth. The array's job now here is to manage these references pointing to the respective objects. However, notice that while the array is contiguous, the actual objects may be scattered at different memory locations in the heap. So I have not shown the heap here, but just imagine. So it's like a bit having a bookshelf where the books might not be in a consecutive order. This non-contiguous arrangement allows for more flexibility and efficient memory usage. So in a nutshell, ArrayList cleverly uses this array setup to store references, making the array contiguous for quick access. But remember, the objects it points to may not be in a contiguous manner in memory. This dynamic structure is what gives ArrayList its versatility. As we continue our journey, keep this visual in mind. Understanding how ArrayList manages its underlying array is crucial for optimizing your Java code. Now, let's delve even deeper into the intricacies of ArrayList. If you got any questions, drop them in the comments and let's dive in together. Now let's talk about LinkedList. LinkedList relies on nodes, each pointing to the next, creating a dynamic chain. So in summary, arrays offer a compact contiguous memory setup, while ArrayList and LinkedList explore non-contiguous, more dynamic approaches. Understanding this memory storage nuances is key to choosing the right tool for the job. Now let's explore further and unveil the intricacies of these memory storage strategies. Let's talk about a crucial aspect of these Java data structures, their expandability, which is our next difference. You know, the ability to adapt and grow when your code demands it. Here we are diving into the expandability factor. Now let's start with our trusty arrays. Picture them as a fixed size container. Once you set the size, that's it. If your data outgrows the container, you're out of luck. Arrays don't have the flexibility to expand or contract based on your needs. Now let's quickly shift our focus to ArrayList and LinkedList. Here is where the game changes. Both of these data structures are like superheroes of adaptability. They can expand and contract as needed. For ArrayList, behind the scenes, there is a dynamic resizable array working its magic. Need more space? ArrayLists got you covered. It can dynamically resize its underlying array to accommodate more elements, making it a fantastic choice when your data might grow over time. Now moving on to LinkedList. It's a bit like a dynamic chain. Adding or removing elements doesn't require resizing arrays, as we saw in ArrayList. LinkedList adapts by adjusting its nodes. This makes it another excellent choice for scenarios where the size of your data might change frequently. So, in summary, what we have learned so far, arrays are rigid, like a fixed size box. But when it comes to ArrayList and LinkedList, they are the superheroes of flexibility, expanding and contracting to suit your data needs. Choosing the right data structures often comes down to understanding how your data might evolve over time. So, as you embark on your coding adventures, consider the expandability factor. It could be a game changer in ensuring your code remains efficient and scalable. Got questions or thoughts? Drop them in the comments and let's keep the conversation going. Alright folks, let's tackle a concept that's crucial for optimizing our code. Unused memory, which is our fourth difference. We are diving into how these data structures handle memory when it's not entirely filled with data. First up, we have arrays. Now, arrays can be a bit rigid when it comes to memory usage. Once you allocate a certain amount of memory, it's there, whether you use it or not. As you all already know, to use array, we need to create one with some size. So arrays may end up having unused memory, like having a box that's slightly bigger than what you need. Now let's shift our focus to ArrayList and LinkedList. The good news is both of these structures are designed to be efficient with memory usage. Unlike arrays, they don't have unused memory hanging around. For ArrayList, it dynamically resizes its array to match the size of the data, avoiding unnecessary unused memory. And for linked list, it adapts using nodes, ensuring that memory is utilized efficiently without unnecessary waste. So in a nutshell, when arrays might sometimes have a bit of unused memory, ArrayList and LinkedList are designed to be more efficient, ensuring that memory is utilized effectively without unnecessary leftovers. It's a subtle but important factor to consider as we aim for efficient and streamlined code. As you continue your coding journey, keep this in mind. Efficient memory usage can impact the performance of your code. If you have got any questions or thoughts, drop them in the comments and let's keep this conversation going. Alright friends, we have covered a lot about arrays, ArrayList and LinkedList. Now let's talk about when to choose each one based on specific usage scenarios. This is like having a toolbox with different tools for different jobs. This section is all about usage guidelines. Let's dive in. Arrays stand out as the top choice when you're working with a fixed size list, which is our first topic. Let us discuss the reason behind this. Imagine an array as a neatly organized lineup of storage slots. Each slot is reserved for an element, and the whole structure is predetermined in size. This predictability makes arrays highly efficient and straightforward. Now let us discuss the next reason, which is direct access. When your list size won't change, arrays offer direct and instant access to any element. You can pinpoint exactly where each piece of data is located using the index. It's like having a well-organized filing cabinet where you know exactly which drawer to open for the information you need. This direct access makes storing and retrieving data from fixed size lists a seamless process. Let's go over the next reasoning, which is contiguous memory. Arrays allocate memory in a contiguous block, meaning the elements are stored one after another in memory. This contiguous layout is like having all your items neatly arranged on a shelf, making it efficient to traverse through the entire list without jumping around in memory. Optimized performance is our next reasoning, and let us see why. Since the size of the list is fixed, there is no need for dynamic resizing or managing extra space. Arrays are optimized for this scenario, ensuring that every bit of memory is utilized efficiently. This lack of dynamic behavior while limiting in flexibility actually boosts performance when it comes to fixed size list. The next reasoning is it's ideal for storage and traversal. In essence, arrays are like the reliable workhorse for fixed size list. They excel in situations where the size remains constant, offering efficiency, direct access, and optimized performance. If you need a dependable structure for storing and traversing a list without the need for constant adjustment, an array is the perfect fit. Now let's go over the next usage guidelines. Now let's turn our attention to a specific scenario, which is working with primitive data types. Here efficiency becomes the crucial factor and arrays again emerge as the optimal choice. Let's explore why. Arrays provide a direct and efficient way to handle primitive data. When you're dealing with simple data types like int, char, or double, arrays shine because they offer a straightforward and direct mapping of memory. Each element is precisely allocated the required memory, ensuring an efficient and direct way to access and manipulate the data. On the other hand, when we consider ArrayList, a powerful and flexible data structure, it may introduce some overhead when dealing with primitive data types. This overhead is known as order boxing, a process where primitive data types are converted into their corresponding wrapper objects. Example, converting int to integer. While this process adds flexibility, it can come at the cost of performance. So, for scenarios involving primitive data types, it's advisable to stick with the trusty array for optimal performance. The direct handling of data without the need for additional conversions or object wrapping ensures that you're getting the most efficiency out of your code. So, in summary, when efficiency is paramount, especially with primitive data types, arrays provide a reliable and performance-oriented solution. They offer a direct and uncomplicated approach, making them the go-to choice for handling simple data types without unnecessary overhead. So, when you're dealing with int, char, or similar primitive types, this trusty array is your key to optimal performance. Lastly, let's delve deeper into the world of multidimensional situations, particularly when dealing with matrices or grids. Now imagine you have a 2D structure, a grid of rows and columns. This is where arrays, specifically using double square bracket syntax, become your coding ally, making your life significantly easier. Let us see why. The number one reasoning is contiguous memory, which we have learned in our previous slides. Arrays allocate memory in a contiguous block, which allows for efficient access since elements are stored sequentially, whereas ArrayList involves additional memory overhead due to its dynamic resizing capability. And LinkedList introduces a node-based structure, potentially resulting in less efficient memory usage. Let us go over the next reasoning, which is direct access. The double square syntax provides direct access to elements with a simple syntax like matrix, then row and column. Let us go over this example. X00 gives you access to the element in the first row and first column, which is 4. In a list syntax, you need to use methods like get, set, which might involve more complex operations and hinder direct access efficiency. Let us go over the next reasoning, which is performance. Accessing elements in a multi-dimensional array generally involves fewer computational steps compared to nested array list. ArrayList has to manage resizing and references, and LinkedList has the overhead of navigating nodes, potentially leading to slower performance. Let us go over the next reasoning, which is readability and conceptual alignment. The double square syntax aligns with the conceptual structure of a 2D array, making the code more readable and intuitive compared to nested list. Alright, let's dive into the heart of our comparison and understand how ArrayList and LinkedList handle index-based access. How they let us grab elements from the collection. Imagine ArrayList as a well-organized bookshelf. Each book has its index, making it a breeze to grab any book you want. Here, each index corresponds to a book element, and you can instantly grab any book using its index. This direct access is super quick and straightforward, happening in constant time, that is O of 1. It's like having a well-organized bookshelf where you can reach for any book instantly. Now let's shift our focus to linked list here. It's a bit different. Think of it as a chain of nodes. Each node contains data and a pointer to the next node. Accessing an element in linked list involves traversing from start to reach the desired node. To get a specific element, we traverse through the nodes. This traversal takes time, and the time complexity becomes O of n, where n is the index you're aiming for. So unlike ArrayList's quick direct access, linked list involves a bit of a journey. To sum up, let's look at the time complexity again. For ArrayList, it's O of 1, as you can see on your screen here. You can directly get access to any element with the same speed, no matter the size. On the other hand, for linked list, it's O of n, linear time. The time it takes to access an element grows linearly with the size of the list. So, for fast and direct access, especially when dealing with indices, ArrayList takes the lead with its constant time complexity. It's like having a bookshelf where you can instantly grab any book you want. If you're enjoying this exploration, hit that like button and consider subscribing. Got questions or thoughts? Drop them in the comments and let's keep this learning journey going. Now, the next topic is insertion and removal speed. Here we have our array list, a collection of elements A, B, C, D, and E, each with its designated index. Now let's see what happens when we introduce some changes. Imagine we want to insert a new element X right in the middle at index 2. The array has to make room for it. That's where the complexity comes in. The array needs to be resized or adjusted, and this process takes time, specifically O of n, time, where n is the number of elements in the array. Now, now let's consider removing an element, say at index 3. Again, the array undergoes adjustments and the time complexity remains O of n. This resizing process, especially for insertion and removals in the middle, contribute to a slower time complexity in ArrayList. In summary, while ArrayList provides quick access with constant time complexity for reading elements, that is O of 1, dynamic operations like insertions and removals in the middle can be a bit more time consuming, involving resizing processes. Understanding these trade-offs helps us choose the right tool for the right job. If you're finding this exploration helpful, don't forget to hit that like button. Let's move on to the next topic. Let's delve into the memory consumption aspect, a critical consideration while choosing between linked list and ArrayList. In a linked list, each element represented by a node not only stores its data but also maintains references to the next and the previous nodes, as you can see here. This additional overhead can add up, making linked list a bit heavier in the memory department. On the other hand, so here in ArrayList, each element stores only data without additional references, resulting in a more frugal memory usage. So if you're mindful of memory usage and aiming for efficiency, ArrayList might be a more lightweight option. Consider these memory considerations when making decisions based on the requirements of your application. If you find this breakdown helpful, don't forget to like this video and subscribe for more insights. In the end, it's all about choosing the right fit for your specific needs. If you prioritize quick index-based access and have a relatively stable list, then ArrayList is your go-to. On the flip side, if you anticipate frequent insertion or removals and memory consumption isn't a primary concern, linked list might be the more good choice. Each has its strengths, and understanding the trade-offs helps you make an informed decision based on your application's requirement. Whether you are team ArrayList or team LinkedList, both have their merits. It's about knowing when to leverage their strengths to optimize your code. Okay, so got questions or thoughts? Drop them in the comment section below. Thank you. Let's take a look at our operation comparison slide. We have got a list of operations and their respective time complexities for singly linked list and array list. It's like head-to-head battle, and we are breaking down the strengths of each contender. Let us start with the first, which is read anywhere. First, we will start with the singly linked list. Singly linked list takes a bit more time, which is O of n, as it needs to traverse the list. On the other hand, the array list shines here with O of 1, offering constant time for direct access. The next one is remove at end. So singly list clocks in at O of n linear time to reach the end. But guess what? Array list is quick on its feet with O of 1, which is constant time for operations at the end. Round 2 goes to ArrayList. Now let's see the next one. Add and remove in interior. So that is removing or adding elements in the middle. Both singly linked list and ArrayList play a fair game, both taking O of n time. It's a tie in this round. Now let us go with the next one, which is resizing. So the concept of resizing is relevant for ArrayList, not applicable to singly linked list. ArrayList takes off and time for resizing involving creating a new array and copying elements. Keep this in mind when considering dynamic arrays. So here advantage goes to singly linked list. If we need to find by position, which is our next operation, singly linked list takes O of n, as it needs to traverse to the specified position. But wait, ArrayList pulls off a quick move with O of n, 1, constant time for direct access by index. So another point for ArrayList. Now find by target, which is by value. Now both the contenders play in the same league with O of n linear time. It's a tie here. So as we wrap this head-to-head battle, we can see that ArrayList takes the lead in several operations, offering quick access and efficient operations at the end. However, singly linked list holds its ground, especially with resizing, as resizing is not in the picture, but have their strengths and best choice depends on your specific needs. If you found this breakdown helpful, don't forget to smash that like button and subscribe for more deep dives into the world of coding and algorithms. Thank you.